All right. So the last example that we were looking at this first spectrum, and we said it was the alkene, and one of the peaks was really weird. Like one of the alkene peaks down here had a whole bunch of really weird multiplicity, and so what that kind of pointed to again was this complex, excuse me, complex splitting, right? And it was this pen, it was this right here, this hydrogen right here, that we said would have been split into just this weird pattern down here, right? And so one of the things that was pointed out in that video is that, again, the reason you see complex splitting is because you have multiple non-equivalent hydrogens, and they all split with each other, right? So that proton, this proton right here, what did we call it? Did we give it a letter? We did A, B, C. We're gonna call it D, right? It's gonna be split by the protons at C, which is right here. And it's also gonna be split by each one of these protons on that double bond, right? So you have to basically, and this is way deeper than I normally get on this, but since we're here, we might as well talk about it. You have to basically build what's called a splitting tree, right? To figure out how many lines that signal is gonna be split into. Most of the times you can decipher it based on the NMR and pick out the peaks. Sometimes you can't because it's just too much overlap. But the way that proton should be split is going to split here with C. And so, hold up, let me get this pencil straight before we.
Wait, so when you say split, that's when you say like it'll count one side separately from the other?
It's going to be, you apply the N+1 rule.
Yeah, separately. So the C will be 2 + 1, and then that hydrogen on its right will be 1 + 1.
Yep, and then the one pointed down will be 1 + 1.
Okay.
That's exactly right. So it'll be a triplet. Right, I'm not gonna estimate the coupling constants and all that stuff because that's way deeper than what we want to get for the class. But then that triplet is going to be split into doublets. Each line in the triplet is going to be split into a doublet because of this hydrogen right here. So you're going to have a doublet here, and then a doublet here. And then each one of those doublets is going to be split into a doublet, like so. So each one of these doublets is going to be split into a doublet. And so you're going to end up with 12 lines for that signal. And some of those lines may overlap. I'm not doing the coupling properly, right? But some of those lines are going to end up overlapping. So what you see down here in this signal is 10 lines, right? You see 1, 2, 3, 4, 5, 6, and then a doublet of doublets in the middle, right there and right there. So it's a total of 10 lines, right? So that means that somewhere on this splitting tree that I just kind of estimated, there's going to be some overlap with the doublets that are down here, right? And the heights are going to be different, all of that. Everything is going to be kind of symmetrical. You can see the doublet of the doublets in there symmetrical. And then you can see these 4 lines in right here are roughly the same height. And then you can see the 2 outside lines roughly the same height.
Okay, so when you do splitting, how do you get, like, how did you get 10? Because at first I thought you just count the lines, but then I counted more than 10. Not from the spectrum. I mean, when you do the
splitting tree?
Yes.
Right. So the point is, again, with the splitting tree, like there may be some overlap between, like, say right here, right? If those 2 overlap, that's only, even though the signal should be a doublet for each one, if they overlap, that's only going to give you 1 line. So what I'm saying is, with the splitting tree, we expect to see 12 lines, but there's probably some overlap in the splitting tree. And so some of those lines are going to merge. So if we only see 10 lines here, right, for this signal, that means that two of those lines in that splitting tree probably overlap to give you just one signal. Are you following that?
Yeah, so do we count the lines of the last part? That's what I'm saying. Like, do I count lines starting from the triplet down, or we just count the bottom? Okay.
Yeah, it's just the ones on the bottom. That's your, so the lines on the bottom are the final number of lines in a given signal if it has complex splitting, if you parse it out during the splitting tree. Right, so I know it's kind of sloppy looking, but some of those are going to overlap. So you end up with what should be 12 lines, you end up with 10, right? So what that means is that within that splitting tree, you have some overlap between some of those signals. And that's why some of the lines probably in that doublet of doublets right here are taller than the other ones. You see how the two middle lines are a little bit taller than the outside lines. And then the other part of this is that the spectrum was done using a simulator. So it's not going to give you a perfect approximation when you have complex splitting like that. All right. Does that make sense? More sense?
Yes.
Yeah, I drew it a little bit better down here, but this was me when I was working on this the other day after class. So you're going to see multiple lines, and it's not going to be like a quartet or a triplet, or it's going to be a bunch of different, splitting patterns, but they'll be overlapping with one another. And that's only because this is a situation where you're going to have complex splitting. And then for the other two hydrogens, right here and right here, both of those are just going to be doublets of doublets. But there's some overlap down here. And so you can see, let me zoom in on that. You can see that signal is just kind of hard to read, right? Sometimes that happens, but that's where your other two protons are showing up between those two signals. All right. Interesting, weird, but if you're an organic chemist and you're synthesizing molecules, NMR is your best friend, because it's the only way to really prove definitively that you have what you say you have. All right, let's go to the next spectrum. There's no complex splitting in that one. For B. All right, if you look at B, spectrum B, the infrared says we got stretches at 2959, 1467, and then 767. All right. And if you look at B, spectrum B, we only have these three choices. Right. If it's this, there's no way you're going to have a shift, chemical shift that's as far downfield as 3.5. There's no electronegative atoms in that structure to make any of those protons that de-shielded.
Yeah, it was called me. She called early this morning. She got on there. I told her don't call me before no damn 10 o'clock.
All right. So it's going to be between these two. Can somebody, let me see. Why is it not? The resolution is kind of bad. All right. Can somebody tell me out of B and C, which one do you think it is and why? And it's not just based on the NMR. It's also going to be based on the infrared. If you could tell me that, I'll buy you lunch.
You saying which one we think is like by 3.5?
No. Which compound? Because we can rule one of them out. We already did the spectrum for D, so we don't worry about that. We can rule out A because there's no way you should have a shift all the way down at 3.5. All right, based on A, there's nothing in there that's going to cause that kind of de-shielding. So it's going to be between B and C.
B? Is it
B? Who was that?
C.
Damn, I think two of us said it.
I vote B.
You vote B. Okay, tell me why.
Because the OH. That's what my reasoning is.
All right. They're gonna both have the same number of signals. And the OH may or may not, in this case, the OH is not showing up. But there's something that you can definitively see in the infrared and rule out one of those compounds. Yep. Which one? Okay, let me say it this way. In the infrared, if you have an alcohol, what would you expect to see? What stretch would you expect to see for the alcohol?
It'd be like that. It's like a droopy, like a.
Yeah, you see a droopy OH stretch. I like that, droopy. All right. If where though? Where would that droopy stretch be? Where would it show up?
It would show up on the far
Yep.
far left, right?
What's the number though? We need a number.
Like 3,000.
Oh, about 30. It's really about 32, 3,300.
Mm-hmm.
Do you see that in that infrared data that's given?
Okay. Okay.
Oh, okay.
It's not there. So it's not B. It's actually C. Do you see how you can put the two pieces of data together to come up with a solution?
Yeah.
The infrared is going to tell you what functional groups are present. The 2959, that's alkyl stretching, right? So and other stretches are just, we just randomly pull those out. But that 2959, that's alkyl stretching. But there's no OH stretch, because OH is always at the same region, somewhere between 3,000 and 3,300, somewhere up in there, and it's a broad stretch. And none of these stretches are given as broad, weak, or medium. You just have the stretches, right? So it's not B, it's actually C. Now let's see. Now let's see if we can pick out the protons. All right, so this is C. Oh, sorry, wrong pen. Right? How many signals should we see for that?
5.
So we should see 1, 2, 3, 4, 5. Good. Hold up, my screen. God dang it, froze up. Hold up, let me reshare. Promise you, slap somebody. All right. So yeah, so 5 signals. Which one is going to be the furthest downfield?
The one next to the chlorine.
Yes. Good. Excellent. This one, right? And then what's the splitting pattern going to be?
It'll be 2, right? Wait, you mean like
The multiplicity. How many lines will the signal be broken up into? Whenever I say splitting pattern, that's what I'm talking about. A signal
6.
is 6
Yeah,
lines,
6.
8 lines, 10. Did somebody say 6?
Yes.
All right. And you can see that here, right? It's furthest downfield. And you can see 1, 2, 3, 4, 5, 6 lines. All right, so we're going to call that one A. That's A. What about this signal right here? We're going to call it B.
I have a question right quick.
Go ahead.
About the last one. So since, is that hydrogen on a sp3 hybridized carbon? And if it is, does that have anything to do with the splitting pattern?
It is on an sp3.
I mean, not specifically sp3, but I mean chiral center.
Well, in this case, I guess it would be considered chiral, but again, this is done in a simulation. It's not picking up the chirality.
Okay.
Right? Because then, if that was the case, these 2 protons right here would be by stereotype. That's a great observation. But we're gonna approach it as if it's not, it's achiral.
Okay, cool.
Yeah, very good observation. All right, so B, where do you think B is? And what should the signal be split into?
It should be 3. So upfield.
Okay, it's gonna be further upfield. Yeah, I agree with that. And it's got neighbors to the
Yes.
left and neighbors to the right.
Oh, so it's 4.
Mm-hmm. So it should be a quartet. Is that right?
Mm-hmm.
Let's see if we can find a quartet down here in this mess. Do you see a quartet?
No.
Really? Y'all are blind. 1, 2,
4.
3, 4. It's kind of overlapping with
Oh.
with what's next to it, but that has the symmetry of a quartet, doesn't it? Like you see how the 2 middle lines are taller than the 2 outside lines.
Mm.
Yeah, it's a little bit wobbly, but it is a quartet. And I apologize for saying you're blind. Don't call the president. He made me feel so bad. He should be fired.
Oh, no.
Y'all just don't know. I'll fly to Jamaica if they fire. I'll be on a plane to Jamaica as soon as I hang the phone up.
Oh, my God.
Say what?
I said, oh, my God.
I'm trying to tell you now. Pew, I'll be gone. Believe it. All right, let's do this set right here. We're going to call that C. What do you think? How many lines? How many neighbors?
6.
6 lines.
So 6 lines. Do you see a sextet down here?
Yeah, the one and yeah, that one.
All right. So what did we say? That was C. Yep. That's C, B. Label them. A. All right. And then what about the triplet?
It's gonna be
That
3.
would be the CH3 on the other
Right
side.
here.
Yeah.
Call that D. Good. And then the doublet is going to be the other CH3.
Yeah.
Call it E. Is this starting to click a little bit?
Yes.
Go ahead.
Okay, so to jog my memory, how do you know when the hydrogen is supposed to break? Because you remember when last time, like it'll be a hydrogen that breaks, so it'll count its left side separately from its right side.
Like what we just did with the complex splitting?
Yes, but then like how do I know? Because that hydrogen, you just the one next to the chlorine, you kind of just added up the CH3 plus the doublet right there.
Right, right.
Adding up the CH3 plus 1 and then the doublet plus 1 and then I don't know.
Right. So for that, it would be, you would just apply the N+1 rule. But in all honesty, if you did a splitting tree and you had a triplet or a quartet, and then the quartet was broken up into triplets, you would see that it will still give you those same 6 lines that for A. But if you did the splitting tree, you'll see that some of those lines will actually overlap. And that's why you would see, that's why you only see 6 lines, because some of the lines in the splitting tree will actually overlap. On that video I sent Wednesday, the last example talked about that, about how even when it's not necessarily a scenario where you have a chiral center or you have like an alkene or some other functional group that causes multiple non-equivalents, you still have it. But when you do the splitting tree, you see that some of your lines end up overlapping. So for these examples, we just apply the N+1 rule and just leave it at that.
Okay.
Yeah. A great question. I could tell this is something that you like. It's bothering you. And I mean, in a good way. Yeah, I mean that in a good way. All right. Any other questions? This is good. I'm glad that we're getting more productive with this. All right. let's go to the next example then. What do you think? We already ruled out 3 of them. So what do you think? Now look at the infrared and tell me what you think. What do you see in the infrared right away?
That 3,000.
3,300 with a broad stretch, the droopy stretch, right? That's telling you that's an immediate giveaway that it's an alcohol, right? And so if you look up here, this is the only alcohol we have. And you can see this little crappy OH peak right here. So like I said, sometimes you can see it, sometimes you can't, right? And then all your other peaks and splitting patterns are gonna be roughly the same. And then this is the hydrogen that's adjacent on the same carbon with the OH group. That's why it's so far downfield. We call this hydrogen, let me draw this out. If it's on the same carbon with an OH group, we call it a carbonyl hydrogen. Right, if it's on alcohol. And those always show up somewhere between about 3.5 and 4.5. But again, this was done in a simulator, so it's gonna give you the perfect chemical shift and all that. All right, any questions about that? So you should be able to go through this one and pick out these signals, right? You can see that quartet right here, 1, 2, 3, 4. Then you can see another signal next to it here, 1, 2, 3, 4, 5, 6. See a doublet, and then you see a triplet. And then down here, you're gonna see that same 1, 2, 3, 4, 5, 6, that same sextet. Right, but what gives it away, because if you didn't have the infrared, you could easily mistake one spectrum for the other one. But the infrared is used to confirm, you know, what the NMR already points out, right? But you can't use infrared by itself because it doesn't give you structural data. It only gives you what functional groups are present. But the NMR, it tells you the connectivity, right? Based on those splitting patterns of those signals, the multiplicity of those signals, that's how you get the connectivity and know what's bonded to what. All right, we okay so far? And then you can see here, this is just a mess, right? It's a mess. And it's the alkyl chain right here. It's a mess, right? You got the two, there's a triplet buried underneath here. I tried to put that in here so it wouldn't confuse you too bad, but there's a triplet buried underneath there. And there's also a doublet for those 2 CH3 groups that are right here, because they're equivalent. And the integration is 6 hydrogens. There's a triplet buried underneath there that integrates for 3 hydrogens. So let's see if we can pick them out. All right. So this signal for these hydrogens, oh, that's a bad combination. For these hydrogens right here, that signal is going to be here, right? That's what it's going to be a doublet, and it's going to integrate for 6 hydrogens. Right, so both of those CH3s are going to be represented by that signal. All right, what about the other CH3? What do you think? What should that be? The one on this end.
A triplet.
Be a triplet, right? So that triplet that's buried underneath that doublet is for this signal right here. I just erased it. right? Both of those signals are going to be on top of each other. And then you have, what about this proton right here? What do you think?
It would be a multiplet, like 7.
Okay. Will it be 7 or will it be 9?
Oh, 9. I didn't double it on the side.
Okay. So if you look right here, I kind of tried to parse it out. There's actually 1, 2, 3, 4, 5, 6, 7. And then there's a, if you look really closely, there's a little shoulder. Oh, shucks, I need to make that pen thinner. There's a little shoulder out here. And there's a little shoulder out here, right? So that actually is 9 lines, right? So you're right. It should be a multiplet. It should be 9 lines, and it should integrate for 1 hydrogen. And then the other signals are just buried on top of each other right here, where you have a sextet and a quartet. Which one of those is going to be a sextet out of these two?
The doublet in the middle.
Right here?
The one you highlighted first.
Right, that's going to be the sextet. You're right. And then this one is going to be what?
Quartet.
Quartet. Good. Good. I think it's clicking, which is great. But that's how NMR is, though. You got to keep touching it, keep doing it, and then eventually the light bulb will come on. All right. So let's do some other, there's another page to this handout, actually. See if we can run through this real quick. And I think that's all of the NMR stuff that we're going to do. So we'll do some more examples on, I got another handout, but it won't be counted. Like you won't have to submit it, but we're going to work through that Monday. And then we're going to take that test on Wednesday. All right, let's see. Let's go here to this. So let's answer these questions real quick. It says, which of the following is generated in a mass spectrometer prior to fragmentation? So before you pound that molecule into pieces, what is the species that you generate, the very first species that you generate after bombarding it with that electron beam?
D?
D, the radical cation. Good. Right. Remember we used this example. We said we had let me get this. We had a CH4, and then we hit it with electron beams, the electron beam, and then it became CH4 or CH4 radical cation, and that was -1 electron. I didn't write it like that, like -1 electron, but that's what happens before fragmentation. You get this radical cation. And then when it fragments, one fragment becomes the radical and one fragment becomes the cation. All right, what about number 2? What does mass spec tell us about any given molecule?
Is it A?
No. A is what NMR tells us about the carbon-hydrogen framework. Mass spec, what does it measure? Mass, right?
Mm-hmm.
So mass spec is going to tell us about molecular weight, size and molecular weight. NMR tells us about the carbon-hydrogen framework. Mass spec tells us about the molecular weight. UV tells us about pi systems, conjugated pi systems that are present. And then what's not listed here is infrared. And that tells you about functional groups. All right. So mass spec tells you about size and molecular weight. NMR tells you the carbon-hydrogen framework, UV, pi systems, and then infrared functional groups. All right, what about the next question? Which of the following cleavage patterns do amines undergo? So let me give you a simple example of an amine. So we got an amine right here. I gave you some cleavage patterns when we went over mass spec, right? You had, if it was branched, it would always cleave at a branch point. If it had double bonds, it would cleave at an allylic site. And if it had functional groups like amines or ketones or oxygen, like a hydroxyl group for alcohols, there was one specific cleavage that those types of compounds underwent. Anybody remember? Let me give you a hint. Another hint. All right, and it always cleaves here, next door. It's alpha cleavage. That's one of your main fragmentation patterns for mass spec is alpha cleavage, and it's always adjacent to whatever that functional group is. Y'all missed the hint. See that?
I was thinking that. I just.
You should have said it. Homecoming. I'm trying to get some homecoming spirit, but y'all missed it. All right, so it's adjacent to that functional group, whatever the functional group is. Let me zoom in and fix that. Right, so that's what alpha cleavage is. It's next door. So here's a great example. It says draw all the fragments from alpha cleavage, right? Only, right? Because if you have alcohol present, then you can also do dehydration, which we talked about already. But it says draw all the fragments from alpha cleavage. So the way you approach a problem like this is to find the functional group, which is right here. And then the bonds to the left and to the right are the bonds that get cleaved. So you'll break that bond, and then you'll break that bond. And then for the ketone functional group, it's the same idea, right? You're going to cleave here and here, right? Not all at the same time, right? But you do one at a time, so you should get a total of four fragments. 8 fragments, sorry, because each time you fragment, you're going to get 2 pieces. Are y'all following that?
Yeah.
Yeah. So let me do this one. So you'll get this plus this. Right. That's 2 fragments that'll come from this cleavage right here. And if you cleave it on the other side, you're going to get this plus this, like that. Are you following? And then each one of those is going to be either a cation or a radical. So in this case, I'm going to put the radical right here because remember we talked about that being based on stability, right? And then you would do the same thing for the other side. And over here also, right? Same thing. You would cleave here, here, and then here and here. All of those are what we call alpha cleavage. You just cleave the bond that's adjacent to the functional group. I could have cheated and used my white pencil and just whited the bond out like that. But all right, so you're gonna just cleave here. Any questions about that?
You said we should get 8 per thingy? compound?
Well, in this particular case, yes, but that's not always the case.
Okay.
It just depends on what the structure is. Makes
And
sense
then
or no?
I'm sorry, on that first fragment you did with you putting the radical on the
Carbon?
yeah, would the other one just be the same thing but the radical switched over?
You mean on the bottom example or which one?
Just the first fragment you did?
Yeah.
So the other, I guess, version of that would be the radical being where that carbon connected to the OH?
Yeah.
Okay.
But see, again, when you think about like stability of those fragments, right? The OH, if you put the plus charge where the OH is on that carbon, then you can do resonance and stabilize. That's why I put it there, as opposed to putting the radical there.
Does it matter? Like, say if I did that, but I put the plus on the other one, would it be wrong?
Well, for the scope of what we're talking about, no. But under normal circumstances, you got to think you're making a primary carbocation with no stabilization, as opposed to making a primary carbocation on the other side where you can stabilize through resonance. Yeah, but no, for what we're doing now, no, I wouldn't penalize you for that. All right. All right, let's go here. It says choose an absorption value that matches the indicated functional group. What do you think for the ketone? $1,700, 1680, 3500, 1150. What do you think? It's gonna what three can we rule? What two can we rule out?
1700.
Say that again.
Ketone? I vote 1700 for the ketone.
1700. I agree. I agree with that. What? So what about the alkene?
1100.
They're both the same. 1680. Did somebody say that? Because you know the alkene and the ketone are a couple in the same place.
Oh.
Oh, because of the power?
Because of the power. All right. What about the 3500?
Alcohol.
OH straight. Droopy. I've never heard anybody say that, but I'm gonna keep using it. I'm still in that. I like it. And then 1150 will be this, right? The CO single bond stretch. All right. All right. Any questions about anything so far? So I'm gonna let you do this last one on your own. It says calculate the molecular weight of each of the following molecules. So all you do in there is add up the carbons, hydrogens, oxygens, whatever. And then it says give the M+1 value, which is what? What is M+1? In a mass spec. What is the M+1 value? What does that mean? So the M+1 plus 1 in the mass spec is whatever the molecular weight is plus 1. For the mass, plus 1. M plus 2, I don't know if we remember we talked about that or not. M plus 2 is only for halogens. Right, so if there's a halogen present, you'll see an M plus 2 peak. So this molecule right here is definitely going to give you an M plus 1 and an M plus 2. You'll see both.
Wait, so then that means that we have to do both? Or only if you find halogens, you only do M plus?
Yeah, M plus 2 is only for compounds that contain halogens. So you're going to do both, right? For that one, you're always going to get the M plus 1 because that's your isotope peak. But if you have a halogen, then you're going to have an additional isotope peak for the halogen. So so whatever the mass is, you're going to see, let's say the mass of that is 185 grams per mole. And in the mass spec, you're going to see 186, which is the M plus 1, and 187, which will be the M plus 2. All right, any questions about that? And then you just do your fragmentation pattern, right? And all of these are just going to do alpha cleavage, either alpha cleavage or allylic cleavage. Because right here, you got a double bond here. So the carbon next door, that's the bond that you're going to break for that. Right? Or you can think about it being alpha cleavage to the halogen. Either way, it's going to break it there and there. Right? And the same thing for the alcohol. And up here for the carbonyl, same thing. Gonna cleave alpha for the ketone. So I just gave you half of the problem right there.
I was just going to say that.
Yeah, I just gave you half of it. All you got to do is calculate the molecular weights and then give the M plus 1, M plus 2, and draw the fragments.
So I have a question.
Mm-hmm.
So since you had went a carbon down to break due to the pi bond,
Mm-hmm.
it wouldn't be the same for that function group with the oxygen?
No.
So it's only alkenes is when you'll go down.
Yeah, the alkene, if I'm trying to think if we, no, I did. I'm sorry. That was it was on the mass spec PowerPoint, but if you have an alkene present, it's going to cleave at the allylic site. So the carbon that's allylic is adjacent to the alkene. So it'll be this carbon right here.
A carbon. Yeah.
So that's where you're going to cleave from. You're not going to cleave here like that, right? We're going to cleave at the allylic site. All right, any other questions? So I want you to finish that one on your own, and I'm gonna write it next to it. This is 10. All right. So if there's no more questions, I'm gonna stop and let y'all have 11 minutes of homecoming freedom. And leave it. I never stop early for homecoming or cancel class. So this is a first.
Okay. We must be special.
Special. Y'all are special. And we only got now how we only got 14 people and there's no events on campus. Everything is virtual. I guess it was a virtual party last night too. What is it? The 20-shot challenge? I saw that somewhere.
A 20-shot challenge.
So let me start with